We're going to start talking about the two main ideas of inference. One of the main ideas of inference is a confidence interval. The goal of your confidence interval is to give you an estimate on where your population parameter is. Typically, with what we're going to be looking at, that's going to be your population mean, which is your mu. A second common type of statistical inference is called test of significance. The goal of the test of significance is to assess if there's evidence to support a certain claim about your population. Typically, with what we'll be looking at is if your mean of your population is different than the mean of your sample. So once again, when you're trying to look at confidence intervals and test of significance, with a confidence interval, you're really wondering what is the mean of the population. With the test of significance, you're wondering, is the mean of the population going to be larger than a particular value, equal to a particular value, different than a particular value, or less than a particular value? In other words, we're collecting data on a sample. We're looking at that data, we're analyzing that data, and drawing conclusions from that data so that we can infer something from that sample in regard to our whole population. Now, when we're dealing with inferential statistics, we're really going to be using probability. We're going to say the probability of something happening is such, or we're going to say the probability that your mean is between these two numbers is, say, 95%. Now, whenever we're looking at our inferential statistics, we always need to be dealing with a simple random sample. We need to officially be dealing with perfectly normal data, but in all practical purposes, if it's roughly normal, we'll be able to go from there. And in this chapter, for what we're looking at, we're going to look at the situation where we don't know our population mean, but we do know our population standard deviation. And you might be wondering, well, if we know the standard deviation, how come we don't know the mean? Well, for the most part, what we're looking at in this chapter is going to lead us into a more applicable application in the next couple of chapters that are used more often. But this is an introductory chapter to help you get used to the idea. And it's going to tie into some things that we've done before. Now, the whole idea of looking at our sampling distribution. Remember, our sampling distributions are when we take repeated samples of a certain size of our population and plot all those means and basically make a histogram and are able to smooth it out. Remember that the mean of all your averages from your samples here is the mean of the population, and your standard deviation of your sampling distribution is sigma over the square root of n. Now, we don't actually know in this section the mean of the population, but we're going to try to be estimating it from our samples. And once again, since the standard deviation of our sampling distribution is sigma over the square root of n, it's not spread out nearly as far, and once again, for the area underneath your population curve or your sampling distribution curve to both be equal to 1, since it's narrower, it has to be taller. Now, when we're looking at the idea of confidence interval, basically we can say that, well, because of the 68, 95, 99.7 rule, that roughly within 2 standard deviations on each side of your mean, you should always end up capturing the true mean of your population. So if you take a look at a total of 20 different samples here, one of those samples out of the 20 will not capture the true mean here in black. The other 19 will, and 19 out of 20 that capture it ends up being your 95%. That is on average. The red dot here means the mean of your sample, and the arrow on each side of that red dot represents the 2 standard deviations away on each side of your sample. And once again, the red line represents your mean of your population that we're trying to capture and understand. So let's consider eggs. Brown eggs are normally distributed with a standard deviation of 5 and a mean of 65. We know in a dozen we would have our 12 eggs, and that's going to be our simple random sample. Well, for our sampling distribution then, since this right here is with individual eggs, our sampling distribution should have a mean at 65 and a standard deviation of 1.44, which is our 5 here, divided by the square root of our sample size of 12. Therefore, when we go ahead and just look at the middle 95% of our sampling distribution, we should be 2 standard deviations on each side of our 65. So we should be 65 plus or minus 2 times our 1.44, which is our 2.88. So 95% of all of our eggs should fall within 65 plus or minus 2.88 grams. Now, if we're looking at white eggs, and there, for a dozen white eggs, the mean of that dozen is 770 grams. So therefore, when you divide that by 12, you get 64.2 grams per egg. Still with the same standard deviation of 5. And so if we wanted to be within 95%, or all the eggs to be within 95% of our mean, you would go your mean plus or minus 2.88, which is double your standard deviation, because it's 5 divided by the square root of your 12, which is at 1.44. But we're looking at 95, so that's 2 standard deviations, so you get to double that 1.44. So you're 2.88 units on each side of your mean of 64.2. Now, with a confidence interval, you're given a confidence level, typically a 90% or a 95% or a 99%, that tells you the probability that your estimate, and your estimate comes from the mean of your sample, plus or minus your margin of error, and we'll be talking more about that in a little bit. But your confidence level tells you the probability of capturing the true mean of your population in repeated samples. Now, what does that all mean? Do we have to go ahead and take many, many repeated samples over and over to build our sampling distribution? No, we really only have to go ahead and take one simple random sample of a certain size, and then we can use that for our confidence interval. So we could say that 95% confidence that our mean would be within 2 standard deviations of the mean of our sample. Now, we'd have a 95% chance of capturing that true mean of our population somewhere within that 2 standard deviations on each side. Now, 5% of the time when we do that, we will not capture the true mean of the population somewhere within that 2 standard deviations on each side, like this one here, because the black line's the mean of your population. But you notice 19 out of the 20, which is 95% of the time, we did end up having the green bars go through that red or the black line, which meant we captured it. And typically we want to use a 90% or higher confidence because we want to be quite sure of our conclusions. Now when we go ahead and capture, or not capture, but do our sample, and make our 95% confidence interval, which gives us our success rate. We don't know if, for that one particular sample, if we really captured the true mean, which we know we would happen 95% of the time, or if we happen to be that unlucky 5% and missed our true mean. But we could say that we are 95% confident that the unknown mean of our population lies within 2 standard deviations of our sample mean, either within 2 standard deviations below up to 2 standard deviations above. In short, we would say we got these numbers using a method that gives correct results 95% of the time. So here's our confidence interval applet. It's set at 95. We just did a simple random sample of 50 samples, and you can see that we ended up missing a couple of times. And we do that again, and the overall percentage is down here, and we've done a total of 100 so far. And we continue to watch this, and as we continue to do this, you'll notice sometimes you're going to get more misses than you do on other times, but once again, it's random, and we would expect that. Now, confidence intervals are often written in the form of your x bar, the mean of your sample, plus or minus your margin of error, where m is your margin of error. Now, sometimes it's also written in the terms of your 2 endpoints, where your first endpoint is your mean of your sample minus your margin of error. And then you would say it would go all the way up to whatever the mean of your sample plus your margin of error is. Like you might say it's from 114 to 126. Now, your confidence level is really the area underneath your standard normal curve between the 2 cutoffs here, where the distance from your center out to the cutoff here is referred to as your margin of error. We know the area underneath your whole standard normal curve is 1. So the area in each tail ends up being 1 minus the center, but each tail only has half of it, so that's why it's divided by 2. Once again, we will need to standardize our data. To do that, once again, it goes back to the Chapter 3 material of the z-scores of taking your x bar minus your mean over your standard deviation divided by the square root of n. And once again, your z-score tells you the number of standard deviations you are above or below your mean. Now, we can have different confidence intervals because we can have different confidence levels. Your confidence level is your C value here in the center. In this case, it's 80%. Now, when you take a look in the back of your book, inside your back cover is Table C. At the bottom of Table C, you'll see a Z star or Z asterisk. That tells you your Z-score that you need to use for a certain confidence level. So for a 90% confidence interval, it would tell you which your Z-score should be. So you don't have to try to find it or approximate it in the middle of Table A. This Z star or Z asterisk times your sigma over the square root of n is referred to as your margin of error. So your confidence interval is x bar plus or minus your Z star sigma over the square root of n, where the last part's your margin of error. Looking at Table C once again here, your confidence levels are listed on the bottom. Right above it is your Z asterisk, which tells you the Z-score you would need to use.